penultimate meeting of the CCS for this season. I will say some words about the next meeting in May, at the end of this session. We're grateful actually to our speakers today for standing in at rather short notice, since we had to reschedule things because of the ailing Pegasus. The subject is IBM, Hursley Park, software, and I think more specifically CICS. Is that right? Something like that.
CICS and Geoff.
That's focus on CICS. Okay, so delighted to welcome Andy Krasun, first speaker, and he'll be followed by Geoff Sharman.
Thank you very much. Good afternoon. Is that working? Good afternoon, everybody. Lovely. Well, it's lovely to be here. And as you'll see in a minute, this library reminds me of the library at Hursley Park itself. Same sort of thing with the balcony and everything else. Unfortunately, the library at Hursley's got the same problems. Not quite as Pegasus, but it's falling down. So the balcony is unsafe. So that's that. Anyway, there's my subject for today. I hope we're not overlapping too much with Geoff, but you know, we worked together for 35 years, on and off.
Well, so we actually joined IBM the same year and left on the same day.
Yes. And no, he's no relation. Anyway, to get on, because as Geoff knows I can talk too much, here's what I'm going to put up as a couple of caveats at the beginning. Firstly, this is my view, it's been looked at by other people, but I haven't put it through any formal testing or anything else. Any errors are mine. I can talk for probably a couple of days on this, if I really put everything in. And finally, as most of computing, but IBM in particular, everything's full of 3-letter acronyms, 4-letter acronyms, and even nested 3 and 4 letter acronyms. So, trouble is, as I say, that the expansion of the acronym into words just doesn't help you either. So we'll try and find our way through this gobbledygook in a minute. So here is Hursley House, the normal picture that everybody sees in the springtime. And this is, as Jeff Robinson used to say, it's a bit like CICS. The original house was the bit in the middle. Then as they got more money, they added pieces to it. Obviously, these are new features or new versions of the house. And then they added stabling and God knows what else. And so that's the picture that most people normally see. So when did Hursley first hit technology? Well, it was during the Second World War when Fairey Supermarine were bombed out of Southampton, in fact Worcester. And they moved the design shop up into Hursley. And so that's where Hursley first hit this thing. And obviously it was an MOD job, so rather than do anything nice, everything was just covered in plywood. All the old Wedgwood stuff in the walls, everything else was just covered in plywood. And that's what actually IBM bought a little later in the story. So that's Spitfire, and that was the anniversary flypast of basically most of the remaining Spitfires around in 2006. So, quick bit of background. IBM started development in the mid-50s. And just like everywhere else that's running a business, why was it a good thing to do in Britain? Well, Britain was cheaper than America. So that was a good start. And as I said, they started mainly with engineers because when you think about it back then, most of the world was hardware, and you had a bit of grotty software to the top of it, so you might be actually able to do something. So, as I said, IBM moved into Hursley 1st of December 1958. Now, the original bunch of people that actually were employed by IBM for this were all Cambridge people. So they looked for a place in the Fenlands, but They couldn't find one, so they went down to Hursley. So what did it start out? Special European projects, and their own processor called SCAMP. The thing about SCAMP, the major piece of injection of technology into the world, was it did overlapped I/O. So the I/O was sort of offloaded immediately away from the main box. So IBM, like everything else, ran a sort of contention system. So every laboratory that started up built itself a different type of machine. The 1401s and 3 were basically COBOL. 70440 was also COBOL. These were much bigger machines. 704, this was a valve machine, that was a transistor version of it. And the scientific ones were the 709, 7090, with Fortran in it. And I hope I've got all the capitals correct. Fortran in this age were capitals, and then a little later becomes just one capital and then lowercase. So, and then process control, which was probably quite new in those days, 1710. And those later became 27 and 37. And the IBM telephone exchange was one of those things. So there's Hursley Laboratory in 1958. The entrance is still the same up there. And so that it's really rural, if you see what I mean.
And it actually says IBM British Laboratory.
Yes, that was before that some educated Americans as to what Britain was and what the UK was. So, but this is sort of some of the acronym soup that I'll talk about. So, as I said, the words don't help very much. All right, there's a lot of customer and distributed and telecommunications and PL1 and good old OS2 at the end there. So if you want to go through these later, you can, but I'll try and mention more what they did rather than what their horrible IBM name was. So 60s, and you can all tell me about this as well, is, well, I programmed my first computer in Oxford in 1963, which was a Mercury. So I can remember back to about that time. And of course, in America there was the bunch. And in UK we had, as I've been hearing today already, ICT, English Electric, Leo with Lions Electronic. And then their software on there was basically autocoders, whereas IBM was COBOL, Fortran, and of course Honeywell stuck out for Algol, for what I remember, as their main language. So with this sort of a contention system, there were more different types of hardware floating around IBM than they really wanted. And so they suddenly found that the cost of programmers was part of the bad side of the profit equation. So they decided that they'd make this one great jump and go for the solution, which was System 360. Well, it was announced in '64, because I was in these IBM research labs in Rushlikow when that happened, and it was quite neat. Basically, each of the labs had picked up one of these things. They said, this is the instruction set. Now, what hardware you use to build it is up to you. And obviously, a range 20 at the bottom, and the 91 was up at the top end. The interesting one in the middle of all this is the 67. If you haven't come across it before, it was a
317 drag.
Yeah, it's a virtual addressing 360. So it had virtual addressing back in '64. Yes, well, they all came out of Cambridge, really. Yes. 4K to 1 mega memory, which of course, in those days, a mega memory was $1 million. So I remember when a whole mega memory came in through the door in Hursley, it was a great day of rejoicing, you know, that something might run faster. And a key point about everything in 360 was the peripherals were all buffered. Everything was buffered off so that when you hit a key on a keyboard, it sat on the keyboard until the actual action button was hit or the function key was hit. So it made quite a difference. And then, of course, we hadn't solved this bit. Everybody started to write their own operating system. So TOS and BOS, tape operating system, and basic operating system, etc., etc. So I think everybody knows what a 360 looked like. 32-bit line word and 24-bit addressing. And even I can remember when I joined IBM in 1968, someone saying the next year is we're using a bit of addressing up every year. So by 72, we're going to be out of address space. And actually, that's almost exactly what happened. Hardware protection between regions. Regions are a bit like processes in OS2 or in Windows. Buffered I/O. And first time I ever really saw a method being overloaded was everything, all the data passed through a data control block, DCB, which would do every device encrypted. So you can just guess what it looked like as a thing. Everybody had a few fields here and a few there. It was an incredible mess. And key point, of course, was the software was bundled with the hardware. Come back to that again in a minute. Now, Hursley's early involvement was obviously, before you could run 360, you had to have an operating system. And so they built a simulator on the 7094 sub-app. The Hursley contribution was the Model 40. And you see here John Fairclough, who was the manager of the whole thing, of course, chairman, president of the BCS. Later, Sir John and manufacturers, scientific, everything else. And he'd come from Ferranti. In fact, quite a lot of people had come from Ferranti. It seemed to be Ferranti and Cambridge were the two things. Once you had those two, you could get in. This, I believe, was really the first soft machine. It didn't do a lot of the instructions in the hardware. It was done on sort of a microcode, in quotes, with something called transformer read-only storage. So depending on which way a circuit went round some ferrite core, was you've got a switching mechanism. So that was the 40, sort of middle to bottom end of the range, very successful. Then they messed with that to put scientific instruction set in there, so that became Model 44, and that was the first floppy disk I ever saw. So in 1968, 69, had a floppy disk on it for loading the microcode. And then that software machine became all sorts of other things, communications controllers later, when they reprogrammed it to do that sort of thing. And from Hursley was the random generator of PL1 programs, and I think a certain Cliff Jones had quite something to do with that, and the PL1 compiler. Well, PL1 in the end came to Hursley. Of course, like all languages built by committees, it was a committee thing. So, starting out with this committee of 3x3, as it was called, but oddly enough, there were 8 people. It was supposed to do both COBOL and Fortran, and systems programming. So it had pointers, it had do loops, if then else, all that sort of thing. And there's just a list of all the things. And later on, we got preprocessors, pointers, record I/O, which is pick up a piece of storage and bung it off to a disk, rather than stream I/O, which is pick up a value and print it somewhere. So it had almost everything you wanted, but it was just like Betamax. So the first implementation from Hursley was the F compiler. It was designed to run in a 64K box. Software came out just like Hursley House in bits, a bit more and a bit more and a bit more. Of course, the only language you had around at the time was pure assembler, and version 4 shipped in 68, and 68 is a key date because that was the date both Geoff and I joined IBM. So by this time, a little earlier, everybody had decided this code base was just a bit rough for having many more releases. So they had some idea and sort of said, right, what we will do is start 2 new products. Good way of doing it. In fact, start 4 products. And you will remember what it was like. If you were lucky if you got 2 or 3 runs a day. So you wanted maximum amount out of the run, right? But then you wanted an optimized piece of code to run as fast as possible when you were in production. So this was when the idea came up of pairs of compilers. All right, so the checkout did checking and tried to do that sort of stuff very quickly. In fact, I think the objective was to do it at a third of the speed of the PL1, a third of the time of the PL1 compiler. So you compile 3 times faster. You ran slower because it was an interpreter. And then the optimizer, Hursley, was going to do the small one, and Boulder, Colorado was going to do the big one. Then, of course, the time came and somebody finally said, why are we spending all this money? So in the end, they chopped the Berblingen checker and the Boulder 100K optimizer and left the other 2 in place. So optimizer writes compiler, but it was written in assembler macros, optimized assembler macros, which was the thing that their management team liked, and so that's what they went with. The interesting thing was that they did it on typewriter terminals. For the first time they got away from the good old punch card. It was all done on terminals. This was 1968.
Usually a system called ATS.
Yes, ATS was the...
Actually word processing system.
Yeah, with word processing system, and someone had written a nice little bit of code on the back end to fire the stuff into the job reader. I mean, it's fairly easy. So the usual way that people make things go faster, you avoid doing what the operating system does and do it yourself. And so it always happens the same way. Almost every operating system I know, that's the way that people get speed out of them. Better register code, generation phases. And one of the things about having 16 registers to play with, everybody says, oh, how are we going to optimize the use of these 16 damn registers? All right? Instead of saying, well, if we only had 1, we'd do it this way. And if we had 2, then we might do it this way. So you can go and look at the papers at the time of people writing register allocators and things like that. And this was the time when, I can't remember when the shit hit the fan, but the first of the antitrust suits came up. About 1970? Something like that. Well, this shipped as a program product because of it, didn't it? It was going to be part of the operating system, and then up came the antitrust suit, and everything had to change. We were going to charge for software separately. And that was a major thing. And at the same time, in came all the interface documentation. You were not allowed to talk to another IBM product unless all of that information was passed, that anybody could have it. It was open information. And so there was always a big fight as to what you actually put out into the public domain and what you didn't. So that provided, we spent our lives when you're doing things later in lawyers' rooms. Can we do this? Can we fiddle this? Can we break, you know? We spent a lot of time with those lawyers up in Hursley House. Checker was where I started out life. Was written in something called BSL, which was a very simple PL1 syntax, pointers, simple do loops, and if then else, that's it. As I said, what we were supposed to do was compile what was 4 times faster than F, and find syntactic errors and also semantic errors much more cheaply. Someone had a bright idea that common routines like talking to disks and things like that should be the same between the 2 products. So what does that mean? That meant you had a compiler over here which produced object code. You had a compiler over here produced object code. Now they both want to use a library. So you have to have a common interface. So therefore that interface had to be defined because of the lawsuit. Therefore it became 3 products. Compiler A, compiler B, and the common runtime library. So that's sort of, just to say what happened to us, or me anyway, there were about 1,000 maths graduates in '68, of which Hursley employed 100 of them in one go, bang, and a few physicists as well.
Expecting to get 60 acceptances.
So, how did we make that thing go as quickly as it did? Probably the only compiler I know that does it all in 3 passes. You know, large amount of fix-up, because key punches were still around. There were no spelling aids or anything like that. So if you put RAED for read, and you put it in, you'd have that be the end of one run, really. You wouldn't get much more out of it. So we respelled things and we did various things. We also formatted the source, which was quite new at the time. And the interesting point was that it was an interpreter working on half words. So dictionary references were half words and everything else was broken up into half words, which is similar to other technologies that came later. And it did some nice things like uninitialized variables, which is probably used to be one of the most common errors. So by fitting an unlikely value into every variable at runtime, it would be checked to see if it was uninitialized. And something that became not so different later, but was quite new then, was pointers obviously were 32 bits. So they built these enhanced pointers, which not only pointed to the data, but pointed to the description of what the thing was that was being overlaid on it and what should be underneath. So you could check for attribute mismatches and all of that sort of thing, which is quite clever, really. Version 2, now we were getting online. And IBM's great thing here was TSO, time sharing option. It was a bit clunky, but it worked. We bent this whole thing completely to do things I've hardly ever seen anywhere else. Was you could actually add new statements into your compiled code as you went along. Maybe a little forerunner to a JIT the other way, really ran the other way. Add a piece into what's already there. And so you could put in, you forgot to initialize something, so you could stick in the source that line. So, and when you saved it all, that line will be back in the source, and you can format it and do whatever. So you can actually build programs online as you're going. And oddly enough, one of the test programs we made this time was we each ran different versions of a program which did, what's it, cows and pigs? You know, so many of these, and you tell them how many are correct under each one. You know, you get bulls and
What's it?
well, whatever. Yeah. And everybody had one of these programs, and it talked to the other one through the various multitasking facilities in the L1. And of course, the thing was to beat your opponent. And the idea we came up with, some of us came up with at various times, was at the beginning, the strategy was not to look for the answer. The strategy was to throw as much away as possible of what the answers could be. And then you had to do a switch to go around to looking for the answer. Now, as I understand it, that's a bit like Colossus, or Colossus was programmed to do that when it was breaking codes. Threw away as much as possible to begin with and then came back. I'm out of my depth there with this audience. So, the world was starting to go online. So, Hursley jumped in, and as usual, you had to have 4 different types of it, levels of it, so you could charge different things, etc., etc., etc. The old thing in IBM had been BTAM, which was basic telecommunications, start, stop, then later by sync. And then people like the American Railways, who used the rail tracks as their telecommunications network, said, BTAM's no good to me. I need something to queue the messages up. So I can try sending it. If it doesn't get through, I can do it again automatically. So that QTAM came in on top of BTAM as the access method to queue the messages. And anyway, in the end, it became DOS VTAM. So we'll skip a bit more of that. On the side, there was some other things going on. The Hursley microprocessor, HMP, it was trying to build an extensible language. It had some things common to Similar at the time and C++. Did that sort of thing. There was a concept of objects and things like that. But anyway, it went off to New York in '72. And I was there in '73, but not on this. And later, Ken Davies, I don't know if any of you know Ken Davies, was one of the people that was on that project, then built this thing called CICS later on, which is a building block to what I'm talking about. So anyway, future systems. So having done all this 360 stuff, common architecture, 4 different operating systems and everything else, they said, all right, we better have another consolidation. So we started to design and partially build this thing called Future Systems, FS. Because the consolidation was, you had the high-end stuff, which was 360, but down the bottom you had System 3s and 1130s and God knows what else down there. So they said, right, we'll take all the ideas we've got in IBM and build this all singing, all dancing box that will satisfy everybody. Which of course can't be done, but they pinched quite a lot of it from that intermediate text in the checker. That became the sort of the layer that was new program. The compilers would program to that layer, and that layer would be built in mixture of hardware and software and microcode, just as as part of the offering. So now, because everybody was going down to this common layer, someone had the bright idea, right, we'll put all the compilers together. So Hursley said, well, we're the best at compilers in the company, send them to us. And the people in New York said, no, send it to us. And California, Silicon Valley was just really starting up properly. It was cheaper to go there. So everything got shoveled back there into Palo Alto, just around the corner from the Xerox research place. And as a result of this, we were not a happy bunch of campers. In fact, we were very unhappy.
So I just button and say, this future system stuff, the whole thing was done, wasn't it?
On St. Valentine's Day massacre,
Yeah.
February the 14th, whatever year it was.
But it lived on and became system
Yes,
38.
yeah, that's right. So someone said, we're not giving it up. We'll build it under another name in Rochester, Minnesota.
And it's so cold there, nobody will ever come to work.
So, if we're getting rid of PL1, we obviously need some work. So in the great and good of the higher management, they said, here's 3 products you can have: data dictionary, CICS, or a low-end time sharing system. Well, luckily, this guy had come from IBM UK, Malcolm Beaver, and he looked at this list, and his background was in a thing called BATS, which was the way that all the UK terminals in banks communicated with IBM mainframe. It was a sort of layer on top of BTAP. Yet again, another sort of encapsulation. And he chose CICS, and I don't know if any of you remember it, but we had a great competitor called Shadow. Oh, big fights, big sort of commercial fights over that. So basically, it'd been invented by Ben Riggins in Chicago, who'd worked out that you couldn't afford to start up an address space in the operating system for every transaction that was going to run. So you start to have to sort of consolidate. And he worked out after a bit you could consolidate great chunks of it. And so the way he did it was, of course, built various pieces of code which did things at a much higher level than the operating system. So FCP would be file control program, and it had sort of a DFHFC, type equals write, and some data, whatever. So it was a reasonable sort of lifting of the API away from the operating system up so that an application programmer could actually write the application rather than just systems code to make the thing work. So there are various functions in here that we won't go into, but two key pieces of BMS, the basic mapping system, or basic mapping support, really, which gave you a device-independent way to talk to the plethora of boxes that are out there. Typewriter terminals, printers, video terminals, 24 by 80, 12 by 40, was it? One of them?
Well, the very first visual example was 12 by 80.
12 by 80.
12 by 40, but it was 3270
Yeah.
actually made the something take off.
Yes. And so what happened is, in came the thing, everything was defined to the system. Every sort of terminal that was going to be used was defined to the system through a table. And this is, for example, terminal control table. And as you'll see later, this was an expensive piece of real estate inside the memory, because it was 750 bytes a throw. So you can start to work out what you can fit into a 12 meg machine when you look at that sort of thing. And then each of the applications got attached to the terminal. Data came in, did the application, and went on out again. And so, oops, I've gone backwards, haven't I? Now, our internal competitor was IMS. It started the other way around. It started with a DL1 database, a pure hierarchical database. It was built between IBM and Rockwell, and I think it was for the Vanguard program. Can't remember exactly. Apollo, was it? But it was one of those anyway. It had every part, and every part was broken down into the next part, and on the backs to bytes, etc., all the way down. And it had, yet again, a device independence, which was similar but completely different to BMS, MFS. Same ideas coming up, but different architectures in the machine. And at that time, they had more data integrity than we did. Because CICS at that time, the programmer wrote his own recovery. Whereas IMS had basically it's built in. So here we are, CICS arrives in Hursley. SNA, I'm sorry, is systems network architecture, which was all the connectivity. So LU0 was the first one. They said, oh, this is the answer to everything. Then, of course, that's why you had LU1, 2, 3, 4, 6.1 and 6.2. So, and you'll see some of this coming around. So, as I explained earlier, the interface between the application and CICS used to be these similar macros. Similar macros were bunged into the middle of your, say, COBOL source. You ran it through a preprocessor, yes, and then which generated the real language, and then you compiled that, and off you went. So now, because of this lawsuit, we decided that we couldn't do it that way. So Ken Davis and Peter Alderson came up with this idea of a layer in here, having a common language on top for every, whatever language was underneath. So it was exec CICS read, whether it was in COBOL, PL1, assembler, and like RPG, you know, it's all the same. Then, of course, as you obviously infer from this, exec CICS, the idea of the preprocessor and the language and everything else, went off to Palo Alto with Chris Date, and what happened? You got exec SQL. So that's where exec SQL came from. It came from exec CICS.
But this made it possible to write transaction processing applications in IO language instead of assembly, which is what we
And so, I won't go into it all because I don't have time, but here is the first time we get what I call function shipping, or what CICS calls function shipping. You have an application in address space A, or machine A. You go out, and the table says it's not on me, mate, it's over there. So across you go, comes into a piece of code called a mirror, which mirrors whatever the other guy wanted. Does, for example, a CICS read, picks the data up, flings it back, and up to the application, and the application didn't know whether that file was on that machine or this machine. So that was the first real software patent I ever came across.
So it was the first use of networking to access the right data.
Yes.
It predates network file system and all those things.
By a long way. And also, it not only did files, it did queues as well, because CICS had two types of queuing in it. And of course, since everything went through this one funnel, they were able to put a basic debugger on that pipe. And multiple region was doing the same sort of thing within two address spaces in the same box. So this is now the way that you're able to separate your terminal pieces and all those 750 byte control blocks from your actual applications which are sitting over there. Now what normally went down in the system, and it was running in production, was an application would make an error, write on something else, and the whole thing would come tumbling down. Once it came tumbling down, you had to start the system up again. You had to reinitialize the network first, and then you could build up your CICS on the back. So with this architecture, excuse me, it meant that the applications, if that address space went down, since it had no network attached to it, it would come up incredibly quickly. So it brought in a huge amount of resilience. And then we started on all sorts of other things. Peer-to-peer, I send something from this program and receive it on this side. You know, very simple sort of network protocol, half duplex. And various then one-phase commit. And then 1.7, first implementation, because it'd been designed in IBM with two-phase commit. So, and at the back of quite a lot of this stuff had been a certain gentleman called Geoff Robinson, who you might remember was the president of the BCS.
Yeah. Yes, no. Yes, no.
Yes. Anyway, so then finally, to solve the problem of those 750 byte control blocks, one for everything on your network, We built this thing called auto-install. Oh, shotgun, the wrong way. So when an actual terminal connected to the system and wanted to do something, we would build the control block on the fly. So it became quite sort of dynamic. And this was 85. And then the challenges came. There's so much good stuff in this release. Unfortunately, someone had completely bogged up the testing schedules for the amount of code that was being written versus the amount of people you had on it. And there was by this time I didn't stop being a programmer. I ended up as a customer relations manager. And so I stood, I think is the best way, or kneeled, on quite a lot of chief information officers' carpets all across the States. I mean, when you, we stopped the Caterpillar production lines. We were in the Fed. We almost stopped Manny manufacturers, Hanover, sending its money to the Fed, which you had to do over a certain gap in the day. In the end, they sent a check in a taxi because they couldn't do it electronically. And who's the Intel competitor? AMD. We stopped their production lines as well. So by this time, my knees were trousers were getting worn out, trying to put the bit genie back in the bottle. But we survived, and it got even better. Now, some of you will come across Mike Cowlishaw, built this piece of software, a high-level language called Rex, an interpreter. And what was interesting about it was, it's the first time I've ever heard of, and the only time I think I've ever heard of, someone writing the complete specification from beginning to end before one line of code was written. and what was interesting about it was done without any meetings at all. All the design and interaction over the stuff was all done over the telecommunications network, which was interesting. Database management. Chris Day, who most of you will recognize the name, he actually taught us PL1 at one point. He was working on extensions for database. And so this is Geoff's stuff, so I'll leave Geoff to talk about that if he's...
Right, well, let's just do it now. The PL1 language extensions for database were not accepted, and eventually SQL became a database language, but there was quite a gap before that happened. Another group were working on database management technology, and they built this thing called the binary relational database, which is essentially tables with two columns only. Sorry, I should have done this name. I apologise. Yes. Another group led by Peter Titman built a binary relational database prototype, which is a database with only where the... It's that. Yes, I see what you mean. Sorry. Where the tables have only two columns, and you can synthesize higher order tables from a number of tables having two columns, right? And then yet another group led by Norman Winterbottom, of which I was part, built a second implementation of a binary relational database, which was actually quite successful. I do apologise for this. It had a number of other innovations in that it was interactive, could be used by ordinary people, didn't require programmers. You could create a database dynamically, update it. It had both a user interface and what we call a data dictionary built into it. and that meant you could build automatically put together user interfaces, do full screen user interfaces and so on, without any lines of code at all. And this was extremely successful on internal applications, so we then thought, well, let's launch it as a product. And we went and proposed it to the folks in California as this should be IBM's database product. But funnily enough, they didn't like that idea. They much prefer the thing they've been working on down the road in San Jose. So I'm afraid, although this did actually get out as what was called a field developed product, it had a life of maybe, it had a life of maybe, go back here, all right? It had a life of maybe 10 years, and I'm afraid it bit the dust. But there's still a lot of good stuff in it, and one thing I'm particularly proud of is the fact that Noel and I wrote a paper on triples, and if you now go and look at Semantic Web and see what they're doing, you'll see the word triples all over it. So that's enough of that.
Turn it off. Right, one of the next pioneering pieces of software was a 3730. All right, it was an office box for when the idea came that you should have your dozen typists all sharing data and typing in at the same time, all that sort of thing. We used a box called a 3790, which is about the size of that kitchen table there. And as Geoff Robinson, who I worked with on this, said, this was a triumph of human ingenuity over common sense. The disk was not big enough, right? And the engine wasn't fast enough. And so, of course, what happens is when you start to try and optimize on these things, you write more complicated code, which is buggier, etc., etc., etc. Now, the hardware aside on this is the disk was a Hursley disk called the Gulliver, which had 62 megabytes. Also, this other great thing about it, if you're into hardware, was the read head didn't go in and out, it swung. It was a swing wing architecture. And that was the first of many, many disks that used that same code. So, and also with that came the revolutionary head sensing technology for when you're on the track or not. You know, it reads the stuff and finds its way to the track and whatever. And oddly enough, I was Bob Commander and John Taylor, and I forgot who the other one was. So those three people in Hursley regularly go into IBM dues in America and pick up $100,000 a piece for the use of everybody's use of that patent. And that's all that sort of thing, but it was just, you know, this incredible amount of brain power that went in to make it fit on something it should not have fitted on. There were some other boxes coming along, office boxes, and then of course, when you think about it, you need a centralized system to tie it all together. And there was this thing built in Germany called DISOS. We'd have a distributed office system, is the main words in that. And it ran both on CICS and IMS. As we mentioned IMS later, that was our competitor within IBM. But due to a quirk, certain gentlemen in IMS said, we're not going to build LU 6.2. Remember, that was the last of the LU numbers. We're not going to put that into IMS. So all these office boxes were 6.2. So suddenly we get 1,000 CICS licenses out of all the IMS shops as well. So that was the time where suddenly our numbers are going up like this, so our revenue is going up like that, and everybody's saying, you're the answer to every problem known to man, which was fantastic, because in came the investment, and off we went. Oops. And typical office thing, but the key point about this was the person who signed this letter was Geoff Robinson. Right? It was put into a system on the 3730. It came up to the mainframe. It got reformatted into a different completely different type of syntax, and pushed out to a 6670, which was a copier, TP attached copier. So this was the first letter that ever really went round a proper office system, changing both its input and its output. So quite a lot to do with that. That's one of my little things. Right, oh yes, because while we were in the office, we had young Mr. Wang coming up with the Wang boxes. So that was where the big competition was then. Now, 87, we're starting to get a whole pile of grief from Tandem. They built this, what they called a non-stop system, you know, two engines, two everything, with immediate rollover and everything else. And though unfortunately, I don't think we ever found a customer that used it as a one in the backup. To make it pay for itself, you had to run it as two single systems. But anyway, IBM decided, well, we've got to do something because we're just losing out on the customer selling game. So they came up with this idea of the cheapest place to do a switch is out in the network. So the network control program out here in the MCP says, right, are you there? Right, okay, send all work there. Then if this goes sick, down it comes, and you reconnect and go to your backup system, which is already up and running. And so that's the way it worked. So that was all being built in Millbrook, which is down in the Southampton docks, right next to the largest sewage works in the south of England. It was pretty horrible working down there at times. So meanwhile, back in Hursley, what happens there is CICS has now reached the same thing as PL1 did. It's got more spaghetti than any Italian. And they said, right, we're going to clean this all up. In fact, we're going to clean it all up was the first thing. They still haven't finished.
Yeah, we're going to rewrite it all, yeah.
Yeah, but so they did the main pieces. And they did it into things called domains. And they did storage control and dispatcher, which is mainly the biggest pieces of all of a transaction system. They used Z, so this was the first time that Z hit the real world. And they say it's a...
Can you just explain Z?
Oh, yeah.
Not everyone.
Oh, they don't know Z. Oh, right. It's a language of sorts. Logical language is the easiest way to say it. That you have a certain set of inputs, and depending on which set of conditions, you'll get a certain set of outputs. Unfortunately, in those days, you couldn't run it. You could only just look at it and see whether it did what you thought it would do. So it gave you a lot of good ideas, and it did cut down a chunk of the development. You know, the stuff that people write some code, and they say, oh God, that's wrong. Toss that away, let's have another go. Yeah, it came from Paris, really. Abdul.
While he was working.
Yeah. Yes. And then Mr. Hoare, of course, and various others were all mixed up with it. And Queen's Award to Industry there for that, and it shipped as various versions through 93. Now, as we said, we had MFS in IMS, BMS in CICS. So of course, what you do now, you say, well, you've got to have one piece of code that's going to be the answer to both. So after many meetings, lots of bad language and everything else, it died a death. So they still had another problem, is that the first Hursley colour terminal, in fact the first colour terminal in the world, right, was coming out of Hursley. And they still needed some software to be able to talk the very funny protocol that went to 3270s. So out came this thing called GDDM. And they were able to do stuff like this. And really the main part of it, again, was a follow-on really from Geoff's database stuff, was how do you get applications without any code? So the interactive chart utility was the way they did that. You could just put in your numbers and you'll get nice graphs drawn and all sorts of things, pie charts, skyscraper charts, whatever. So it was a bit like what Excel did about probably 10 years later. And yet again, this is one of my things. OSI was around, it was becoming, somehow someone in the government had said, right, we've got to be open, so if we have open standards, therefore we can buy hardware from anybody and software from anybody and it all fit together. Absolutely no problem. So someone therefore inserted in all the bids for the government is you had to have OSI technology for X400 was the thing they wanted. So there we are, we've got our SMA level and we've got the OSI levels. But roughly the top of layer 5 is roughly where CICS is. So you've got one telecommunications pile up on this way, and you've got the other pile the other way. You can almost talk on the top, almost. So we had to build this OSI package, and we started to look at this and said, we can't do this, we can't afford it. So anyway, 1, 2 and 3 existed already. A German firm had layers 4 and 5, bits of code, all beautifully built from the standard, And of course, what was the answer was, well, plug it all together, put some code on the top, and we've got somewhere. Well, that's what we did. But as everybody knows, that when you buy chunks of code that don't know what's going on up and down, it will form like a sick pig. But it was there, it worked, right? So it was a performance nightmare. And unfortunately, I'm mentioning no names, they're not here, because this was tried to be done 2 or 3 times again. And no one ever learned that just plugging layers on top of layers without one knowing what the other's doing it just doesn't perform. So anyway, here is the eventual thing we had, and I think I mentioned most of the things, DISOS and X400, and as you can see here, this is addressed to me, because I was the manager in charge of that bit, and Geoff Robinson by then had risen to being the IBM UK technical director. Sorry, that is a large lump of celluloid, that's why it's not too neat and tidy, but it's there. So that's what happened. It worked, it wasn't pretty, but we got into a whole pile of bids, which was the important thing. So here we are. Now I can't remember was this Geoff leaving the first time?
Probably, yes. I don't know.
Pat Saltz.
No, not Pat Saltz.
Well, anyway, this is Geoff. Pat Saltz, who later left IBM and went to Sun as their big high honcho in software. Phyllis Byrne. So I think this is when she took over. Unfortunately, that's me.
And I'm in the back row.
You're in the back row.
I'll be in bracket 3.
That you?
No. That's in bracket 3 and I'm in bracket 3.
Oh, that's it. Right, and that's Tony Story,
Yeah.
who got the Lovelace Medal last year.
Yeah.
John Chapman, who you remember became the office manager in Swindon for the BCS. And there's Sue Hodgkinson, one of the inventors of function shipping.
Yeah.
I think that's all the persona that had any tie-in with the BCS and things. Right, now we come to PC time, and after people had finished with the 3279, which was the colour terminal, said, right, what we're going to do, and PCs were coming around, and there was DOS. So the great and the good get together again, and we start to do the great answer to everything, which is build software in at least 3 or 4 places at once, and hack it all together. So Boca had the hardware and part of the operating system. Hursley had the presentation manager, the top layer, which did all talking to tubes, but also was the dispatcher, because that was the only way you could really tie in interrupts from mice and things like that into the whole system. You had to reverse your idea that your interrupt loop was at the top, in other words, rather than at the bottom. And so that's what happened, and so off we went. And our friends in quotes at Redmond, had parts of the operating system, but most importantly, which is something we never realized, was they had all the applications. They owned them, they built them, etc. So OS2 was getting later and later and later, as all these grandiose projects do. And our friends in Redmond, that's why you're worth about 37 billion, I think now, said, I'll siphon some work off, put it in a warehouse, and they quietly built Windows 3 in the background. And so they were ready with Windows 3 when the new Intel came out with. Bang, they did a deal under the covers. And I can remember it now, the shock and the horror and the whatever. And the trouble was, we couldn't sue them. We could not sue them, they were too small. And the lawyers just said, no, we can't do it, you'll have to let them go. And well, the rest is history, isn't it? So that's just a little bit about what happened underneath there. So TCAM obviously was coming to the end of its life, and in good old IBM way, they said, oh well, we'll reduce it, we'll stabilize it, is the great IBM phrase. Standard task force was assembled, the usual list of great and good customers were visited, and the only question they could ask is, where's the TCAM follow-on? Basically the whole of Wall Street ran on TCAM. So this thing called MQ was born, which has turned out to be an incredible success. It runs on 20 plus platforms, and it is the leading solution. And I'm not being an IBMer here, it really is the leading solution for sticking two different applications together, no matter which sort of hardware base or operating system base you're on. Incredible piece of software now. And finally, as we said, the money rolled in, the CICS expanded, CICS 400 on the AS400 series, OS2, MVS, and etc. And on AIX as well. So they all started, and well, different technologies, of course, everywhere. They're built in different buildings, so they all use different ways of doing it. AIX was built from standard operating system blocks. You can guess what the answer to that was at the end. AS400 was built from scratch, and then CICS OS2 was one of the things I worked on for 2 or 3 years. So that gets a very interesting piece about what was clever about it. But there's then that anti-acceptance of saying, well, we want OS2 on every desktop. We don't. We want to run DOS, really. And we only want to just do the display there. And so, what's his name? I can't remember now. We had a weekend in Millbrook. No, it was curly-headed English fella. Lived in Bournemouth. Anyway, it doesn't really matter. We've been trying to persuade these customers to put OS2 onto all these outboard boxes. They said, no, we need something that is small, light, and basically will ship a piece of code up and down from its mainframes down to these boxes. So the CICS client was born. We took CICS OS2 and we just hacked pieces out of it. And in the end, we got it down to 100K. Just, hacking stuff out. We had it running over a weekend. And that then became the CICS client, and Geoff then became the technical planner for that, wasn't you? So, I think, is it over 500,000 now?
No idea what it
So anyway, that's sort of how one piece of software can morph into another, make some money. There's so much I've had to leave out. BDL, the definition language, Cliff Jones again. SNARTAM, first product I've ever heard of was compiled out of the architecture document, with putting the document in as the input and the code coming out the back end. Oh, all that list of things. PT3270G was sort of halfway between a 3270 terminal and a PC. It had a bit of each in it. It did graphics, because that's what G stood for. The hardware side, 5444 was a disk. Functional memory, either a bit is on, is off, or is a maybe. I don't care. Which is the basis of all your address systems in virtual series. So that was a Hursley thing. 3250 was a vector box, vector graphics box. 135 was the next series of 370s. 3290 was the first flat panel, gas panelled terminal. Orange. You had four windows. Really nice box to use. Anyway, Moore's law would have been very useful if we'd all noticed it, because we've had many examples already today of where, if we thought about it at the time, we'd have known certain things about what's going to come in the future. And what I call the cartwheel of technology is whatever we did wrong 30 years ago, we're probably doing it wrong today. And this is a great sort of, ending, is one can and should learn from history. And Hursley was a great place to have a career. And there's Moore's law that you can all have a look at. Well, thank you very much. I've probably overrun and
Can you hear me? Yep.
Nearly.
Nearly. I want to put this up.
Move it up in time.
That better?
Yeah.
Yep. Better? Good. Okay, I just need to fiddle with this machine. Now this, come on, wake up. There. Right, my talk is called Why is Kick Still Alive? Because it's all very fine talking about history, but as you heard from Andy, when we joined Hursley, it was a hardware lab, and it specialised in processors, disks, and displays. And over the period that we worked there, it morphed into a software lab. Today it's a pure software lab, one of probably 4 or 5 leading IBM software labs around the world. And it's very successful as a software lab. And this is, if you like, CICS is still the flagship product, and as I'll show you, it's still making a lot of money. So I thought I would just give you a quick snapshot on where it is now, and then a little bit of hopefully an explanation about why a product of this sort is needed and why it's still needed, and picking up on Neil McGregor's History of the World in 100 Objects. Yeah, I thought I would give you some of the key. I'll go over some of the things you've heard before, but in perhaps slightly more detail. What were the key innovations that CICS introduced to the marketplace that enabled it to continue to be successful? So, this is where we are now. We're at what's called CICS Transaction Server 4.1. On the Z series is the successor to the IBM 360, which has gone through. Thank you. Yeah, the IBM 360 architecture is still alive and well and has been extended many times. Contrary to the belief, the popular belief that the mainframe era has passed, I'll show you that mainframes are still very active. And so this version of CICS was launched last year, and it added things like enhanced support for web services, yes, okay, I think I mean SOA, don't I? Service-oriented architecture, can't remember that. It's still very, very successful. There's also a version of CICS for non-mainframe platforms, which is derived from all those various products that Andy was talking about earlier on, which is now known by this rather horrible name, TX series. I won't say very much more, but it is a CICS system, runs on Unix and Windows. And also this family of products that Andy referred to, CICS client, CICS connectors. This is for connecting non-CICS platforms, such as a web server, to CICS. And as Andy said, that's also very successful. Now, to give you what I mean by success, I'm just going to show you that. That's actually not the Hursley Lab as it exists quite today. It's a picture taken in the 90s. And the major difference is that this, around the millennium, this building here was completely refurbished, inside and out, and now looks rather different. But apart from that, the configuration of buildings is more or less as you see, and there are about 3,000 people working on the Hursley site. So it is a major lab. And there aren't any more huts, trailers, porta cabins,
We were down here on the front.
all those things that we know and love from past years. So, you know, the sort of reaction you get when you present, here's a product called CICS and it's mainframe based and it's successful, is, well, hold on a minute, mainframes died years ago. I never see adverts for CICS programs. One time you could look through Computer Weekly or those types of magazines and scan through the job adverts and you'd always see CICS COBOL programmer wanted. You never see that now. So, and that's usually a good sign as what the market is looking for. So how come you don't see it? And you know, you sure you're not just playing before geese, right? Well, here's the answer to that, right? Did you buy something in a supermarket today, or any of these other things? Because if you did any of those things, you almost certainly use CICS. Right? All the big UK supermarkets, Sainsbury's, Marks and Spencer's, Waitrose, John Lewis, they all use CICS. All their back-office processing is done on CICS. All their interactive stuff goes for CICS. All their point-of-sale machines, right? If you make a phone call, BT, the call billing, not the call routing, but the call billing is done on CICS. If you use Vodafone or Orange, it's actually done on CICS on Unix. If you did, you bought something with a credit card, Barclay card, for example, and many of the other credit cards, the applications are all based on CICS. Almost every UK utility company is running a CICS-based application. So that's just the UK, and then you've got to think about the US and the rest of the world. One of our most fun projects, excuse me, in the era when Andy and I were working on CICS on non-mainframe platforms, was the automation of Chinese banks. And what we had to bid, they had a mainframe-based back-office system doing account management, only in batch, which had to be brought online. And they had quite a lot of branch offices. I'll tell you how many in a moment. But their branch offices were partly, a third running on IBM AS400, I think it was, a third running on NCR Unix something or other, and a third running on something else, can't remember now. And all of those had to be automated, and they needed a branch office automation solution, and that was built on CICS on Unix and probably OS2, I can't remember. But how many branch offices do you think they have in the, let's say, there are four, I think there are about 6 top Chinese banks. But one of them, for example, was the Agricultural Bank of China. So how many branch offices do you think they have? Give me a guess. 50,000. Well, actually, you're a little bit over. It was 30,000. But, you know, if you think a European bank, 2,000 branch offices is a lot. Yeah. 30,000 branches, imagine that. And we also did something for Japanese Social Security, which you probably remember. And that was, I think that was 60,000 Social Security offices. So, you know, and of course their networks were awful in China. So I hope that's given you a reason to maybe some credibility that there is something there to be done. And this was a statement, I mean, this is an understatement because it says in the US alone, actually this was one bank, State Street Bank in the US, told us, well, we're processing this amount of money through our CICS systems every day in financial settlements. So worldwide, you know, obviously the number is probably a bit more than that. So that brings me on to the topic of transactions, which is actually becoming a very fashionable topic again these days, having been out of fashion for many, many years. An awful lot of things that you do in the course of a day involve remote transactions. So how many transactions did you do today? Give me a guess. So far.
0.
Well, I will suggest to you that probably isn't true. Right? But let me do it for myself. Right? I drove to the station, I parked, I paid for parking with a text message to a phone, which was processed by an IT system somewhere, right? I went into the station, I bought a ticket from the ticketing system, that was a transaction. I put the ticket in the turnstile to enter the platform, that was a transaction. Same thing at the other end, I went to the underground, my rail card ticket went into the underground, came out the other end. So, you know, there's half a dozen then before you've even begun. And that certainly isn't everything that I've done today. And I suggest to you that the same thing is true. Now, way back in the 90s, we were trying to calculate how many transactions we were processing in a day, and we came up with a number of 20 billion, which was based on actually internal information we had about the number of computers that had been sold, the number of mainframes that had been sold, and where they were being used and what applications they were being used for. It was no secret at all that probably 3/4 of all mainframes were being used for transaction processing, and we knew what proportion of those were CICS and so on. So we could actually make an estimate. And when we worked at the time, 20 billion transactions was 4 for everyone on the planet every day, which seemed incredible. But looking back at it now with current usage, the number is clearly much higher. You know, no doubt there are third world countries where nobody ever does a transaction of that sort, but in the Western countries the numbers are much higher than that. It would not surprise me if they were in the 20, 30, 40, 50 a day. Was quite a reasonable number of transactions for many people to do. Right, and of course, you know, there's all this stuff now, isn't there? And the numbers here are incredible. And I have to confess that not all of these are on CICS.
Why does Google face with the Twitter thing?
Well,
It's eBay and Amazon. You should purchase things.
it's yes, eBay certainly and Amazon are both transaction-based systems. Google is very interesting. It's actually a read-only transaction-based system because you do a search involves retrieval from SQL databases. And Google's architecture is extremely scalable for read-only transactions. If you try to do real-time updates on it, you will discover it's not by any means optimal for that. And that, of course, is one of the problems that we have to solve in commercial transaction processing because, you know, updates are actually really rather important. You don't make any money if you don't do updates. Now before I come on to that, what I wanted to do was to just try and give you one more answer to this question of what's success. We are willing to go on record with CICS was the first software product to reach $1 billion of revenue, lifetime revenue. But that was actually really rather a long time ago. And CICS is certainly making in excess of $1 billion a year these days. So its lifetime revenues are very much greater than that. And fortunately, we now have some of those other products that Andy talked about, Hursley products, which are also making revenues in that league. So you start to get, you know, the Hursley Lab has revenues of attributable to its products of probably $2+ billion a year, maybe 3 even, which is a significant software business. I think you'll agree. It's not Windows, but it's still a very significant business. But I won't put those in print. Right. So a lot of CICS's issues have been how to survive, and you heard of some of the things that have happened, like all the big changes in networking, from SNA that Andy was talking about, the evolution of SNA, OSI that came and went, TCP/IP that came and nobody thought it was serious, but it stayed, and in recent time HTTP as well. And CICS supports all of those, supports TCP/IP and HTTP today. So that's one of the things you have to do. Actually, the biggest thing you have to do is compatibility. You go back to System 360, the rationale for System 360 was the fact that customers didn't want to rewrite their applications. And the rationale for CICS is exactly the same. Customers don't want to rewrite their applications. They do want to evolve them, but they don't want to rewrite them. They want to be forced to rewrite them. So exactly the same rationale applies. And maintaining compatibility over all these technology changes has really been quite a challenge at times. In fact, now there was one technology change, the one change where we had to broadcast an incompatible change. Do you remember that? And I can't remember what it was now. Yeah, I can't remember what it was now. But I mean, we actually had to signal very clearly ahead of time to customers, this is going to change. You know, in 1-2 years' time, you need to be prepared for it. Economies of scale. Now we went through a long period during the evolution of the PC when everyone thought that economy of scale had disappeared. It was cheaper to use a small machine than a big one. But those days are now well past. And consolidating footprints of machines into ever bigger machines is the name of the game. And that actually pushes the envelope in terms of what's the maximum workload that you can process. And a lot of the work that we've done has been on that. Right? And then, of course, new styles of application development. As Andy explained, we started off with COBOL. We had a major change using exec CICS when it came to high-level languages. These languages are still very much around and in use. There are estimates of something like 160 billion lines of COBOL code in the world. It hasn't gone away, it's still there. But then, of course, C and C++, we were perhaps not quite smart enough, not quite quick enough to the game in terms of object support for object-oriented languages, but we did get there eventually. Java, of course, came along with a huge story about how we supported Java. That was one of the things you didn't mention, which was a lot of the Java technology work was done in Hursley. But, and the very latest, who's heard of PHP? Oh yeah, right. PCS website runs on PHP, I gather. I'm sure it doesn't run on CICS, but PHP does now run on CICS in the latest release. So, of course, we should be going along to some customers and saying, don't run 20 servers running PHP, put it all on one CICS. Okay. Excuse me. I don't hang. Right, okay, one more war story and then I'll go through some technology. Where were you on September the 11th, 2001? Were you? Well, I was sitting in the office like everybody else, hearing through instant messaging from colleagues in the States about all the incredible things that were happening, which we hardly could believe. But 2 days later, I was on an aeroplane because I had a scheduled trip to Atlanta to talk to one of the big US airlines. And that's the point of this story. The plane was very empty, surprisingly enough. And when I got off the plane, I was taken almost from the gate immediately to the airline office for the meeting, and then back to the gate and then home, right? But the airline was, the substance of the discussion was, we've been running our major systems on Solaris, Sun Solaris, and we're absolutely fed up with it. It's so unreliable. What can you do for us? And it turned out they were running a transaction system called Tuxedo, which some of you may have heard of. And Tuxedo was originally developed at Bell Labs, and it's now part of Oracle. But it was orphaned for many years. It wasn't being well supported. This airline built a lot of their own software around Tuxedo to improve its application support and its reliability and productivity, and we were able to show them that CICS could do all of this with very little additional code and give them mainframe reliability as well. And that was a big step forward, not only for them, but for us, because in a mature market, you have to fight for every single license. You don't just pick up dozens a day. So that's the point of that war story. Right, now, excuse me, I've done it again. Right, so history of CICS and 10 innovations. As Andy said, CICS was one of IBM's 3 first price program products in 1968. In fact, the others were, it was CICS, IMS, and a product called GIS that was a reporting program that everyone's completely forgotten about. CICS and IMS are still alive, and IBM very reluctantly agreed to price its software to allow some of the competitors a market. And the price that was charged for CICS initially, I think, was $300, wasn't it? Something like that. $300. So they did charge for it, but only just compared with the hardware, which was a great deal more. But that $300 for a license has grown to the revenue stream that the product has today. So you can see how software business can grow. And without that, there would never have been the investment, as you said, Andy. Without that revenue, there would never have been the investment. So it was crucial to a software business taking off to actually have a price for your product in the first place. And we've done that subsequently with new products that we've introduced. We've sometimes had to argue with customers who say, well, you know, just give it to me. That was the case with the CICS connector. They didn't see why they should pay for that, but we argued and it proved to be crucial. Right, now the others are all technical things which we've actually briefly gone over, and what I'll do is I'll just go through them in a little bit more detail, but before I want to do that, this only goes up to the end of the century, so I want to just talk about the millennium briefly. I don't know if anybody worked on the quote millennium bug unquote. I'm sure some of you did. Twice. Well, isn't it interesting that the press, well, they blew it out of proportion before, but afterwards they just, it was all a con, right? It was all a con. Well, we did put a lot of investment in, but actually our customers had to make far more changes than we did, because all these date formats were in their applications. We had a team standing by as midnight passed. It wasn't you, was it?
I was in the lab, yes.
You were in the lab, right? Nothing happened. Nothing happened, which was good news. Except two things did happen, and these were the two things. One customer reported a bug to us the very next day, on the 1st of January, in what was called statistics collection, which is where CICS can accumulate statistics of running programs, which you can then later query. And they found a bug in statistics collection. So they said, there you are, you see, there was a millennium problem. And when the bug was analysed, we discovered that it would have failed any time in the last 10 years had it been run on January the 1st. But it never was. Because everyone was on holiday. And the other one was at the vending machine in the lab. The coffee machine malfunctioned. And that was a date-related error. So, you know, there was a millennium bug, but some people didn't see it coming. And since then, these are the things that the CICS team has been busy on. As Andy told you, we left around this period here, 2003. So we were involved in some of these up to this point, and not since. But you can see all the modern buzzwords are there. And I'm not going to talk about these things in any detail, but the challenge of continuing to stay with technology changes is still there and isn't going to go away. The latest trends here, this Eclipse-based use, this is interactive application development. You know, that is something we talked about right at the very beginning. PL1, interactive development environment. But of course everything is much more sophisticated now than it was then. But it's the need, you know, exactly the same need is still there. Who's heard of mashups?
Yes,
Forgotten what they are. Well, this is another of those interesting reflections on the history of computing. If you remember, when objects were introduced, the justification, one of the justifications that was cited for objects was reuse. It turned out that rather than writing new programs that you can reuse, reusing the old programs you've already got is actually much more effective and much cheaper. And there have been various technologies for reuse, of which we would lay claim to having introduced some of them. But the latest generation of that is that a lot of web programs are put together by scripting, which essentially strings together lumps of existing program in other languages. And that scripting is what's usually referred to as mashup. And there are scripting languages that have been introduced specifically to do this. And you know, it's all about putting applications together as fast as possible with the least cost. So what I want to do is just talk through the 10 innovations, just a little bit more detail, and then I think we'll be all done. I think I've already said this, that the fact that we priced was critical. The first product reached $1 billion of revenue, and the so-called monthly license charge revenue model really underpinned future investment. Now, again, isn't it interesting? In the recent downturn, if you read the IBM annual report, it told you that 2/3 of IBM's income was from what is called annuity products, what they refer to as annuity products, which are products that you lease rather than buy. And this is an example of that. Even the Unix and PC type software is effectively leased these days, which is full circle to where we were with the hardware 25 years ago, when the hardware was expensive and it was leased. So, this I think is now becoming fairly common with other software products. It's certainly not true with PC products, which are nearly all free these days. But on the servers, I think this approach is becoming more common. Right, now the second innovation, which is almost so obvious that we forget to talk about it, is the so-called pseudo-conversational applicational model. Who's ever heard of this? Yeah. You should have. Nobody else ever heard of it? No. Has anybody heard of stateless applications? Yes. Right. Well, if you know how the web works, which I'm sure you do, that your browser connects to the web server, exchanges some data with it, and then disconnects, that's a pseudo-conversational model. And why does it do that? The reason is that the web server discards the storage associated with your request as soon as you finish with it, and that minimizes the memory requirement in the server and enables it to scale to tens of thousands or even larger numbers of concurrent users without reserving state memory to capture the state of each user concurrently. If you tried to do that, you would jolly soon run out of storage. And it's actually the secret of all scalability. And we now realize that even more than we did at the time. This was the model that for kicks was invented by a guy called Ben Riggins. And it was, he was not the only one. There were parallel inventions by other people. But the idea that instead of doing what you did in the mainstream way of computing in that era was what was called time sharing, where you signed on as a user, you signed on at the beginning of the day, and you had a whole address space in the server reserved for you all day long, or as long as you cared to use it, and that was incredibly expensive. And software that used that architecture would scale to 100 users. In the case of VM, it was several hundred users, but you couldn't go beyond that. Whereas with the student conversational architecture, you could scale to thousands of users concurrently being supported on a single server. So this was not only one of the absolutely critical foundations of Kick's success, but it has been much more widely used since. And it's really the foundation of why the web is successful. Okay, and just as an example, this is the sort of thing that happens in networks, where in 1968 a 50-terminal network was a big network. Around the millennium, we were supporting one of the applications I remember well was an American stockbroker that was offering online stock trading, and they had, I think it was 2 million customer accounts who were authorized to do online stock trading. They certainly, before the millennium, before the dot-com crash, this was a very popular thing to do, and there certainly could be, hundreds of thousands of users at any one time concurrently doing online stock trading into the CICS system. So that's the basis for my claim that this is a reasonable number of concurrent users to claim we can support. Now, I've no doubt that Google and others will claim that they support even larger numbers of concurrent users. It's not hard to imagine that, to understand that. But so that, I'm not going to claim more than we should claim, but I'm going to say that that underlying technology idea is the solution to this kind of scalability. Andy mentioned the exec-kits command level API, which is a macro level API, and what this did was it virtualized the internals of CICS. Up to that point, assembler programmers had been able to see all of the internals of CICS, and they'd actually programmed it by putting bits into CICS own storage areas. A technique that was not only guaranteed to be full of the error prone, but was also guaranteed to make sure that applications were locked into a particular internal structure which you might then want to change. So this exec language effectively provided a virtual environment for applications. And when I say that, I'm saying that with bearing in mind all the other uses of the word virtual, which I'll mention in a moment, because the idea of virtualization and virtual environments has become, again, very, very popular in the last few years. It's an idea that was well understood 30 years ago, and then somehow almost forgotten. But it's come back again. It's a very important idea. And this particular idea of virtual interface was what underpinned a lot of subsequent development. So one way of looking at CICS is as a layer, and although we've heard about the disadvantages of layers, they do have advantages as well. The CICS application up there could only touch CICS. It wasn't allowed to touch the operating system under pain of death. So this meant that the application only knew about CICS. It provided a higher level of abstraction of the operating system, and the principal reason for this was to make application programming easier, but it also had the advantage of bringing lots of other things with it, because we could do things that the application didn't know about. And if you actually look at that in more detail, these days, in a modern data center, you have this middleware layer here, which actually also hides the database and the communication. But you might also have this down here, the so-called virtualization layer, which enables you to be running multiple systems on a single piece of hardware. Is everyone familiar with virtualization? Do I need to say any more about it? The trend in data centers in the last few years has been to take individual server footprints on Unix or Windows or whatever and host them all on a single bigger server, which cuts down administrative overheads, enables scalability, improves, lowers costs because most servers are underutilized. This thing here is a product called VMware, which has become hugely popular in the last few years. It does for some of the non-IBM architectures what the old IBM VM 370 product did. And if you look at the IBM architectures, you'll find that VM is actually built right into the microcode machine these days. And on the so-called Z series boxes, you can run 6 different operating systems straight on the box. So this is it's a very important development, but it's also important to understand that there's not only virtualization at the hardware level, but there is virtualization taking place at the CICS level as well. Right, well, you heard about function shipping, and you heard about Sue Hodgkins and Peter Home, who later went to work for one of the other companies. Tandem, yeah. And that they wrote the patent, which is the basic patent in distributed computing, which is a big claim to make, but I believe it's true. And this idea of accessing the data on one CICS system from another CICS system was in fact the precursor of all distributed computing. I've just had that discussion with George Kamuras, who wrote a book on distributed computing, and he's gone away to say, oh, I need to think about this. Right, and much later, this idea of accessing remote data was extended to support something called exec-CICS link, which is a form of remote procedure call. Now, by that time, remote procedure call was already in use on Unix, and we were in catch-up mode. But that was a demonstration of the capability of that technology. So here's the picture again to show you that an application on one CICS can talk across a network, CICS to CICS, and then to data talking on another, locating on another CICS system. The routing is done by directories, so it's absolutely transparent to the application. It can be reconfigured by the system programmer at any time, and that means that the CICS layer can run on different, and this can happen not only within, not only between 2 separate pieces of hardware, but also different address spaces within a single system. So CICS layer can run on different processes, on different physical systems, different operating systems, so it becomes a virtual multi-system environment. And when you write a CICS application, you're not writing to a particular box, you're actually writing typically to a virtual CICS environment. And in fact, one common way of using this capability is in this so-called 3-tier architecture, which again is now widely used in the web and so on, where the device, whatever the device might be that you're using, talks to a CICS routing region, which then talks to CICS application regions and talks to, finally, a CICS data region, which is running the database. And this gives you all sorts of advantages. You can have, these things can support the type of network failover that Andy was talking about earlier on. These things can be replicated. So, and some customers are running hundreds of these CICS regions, which provides you protection against application failure. If an application fails, this disappears, or could disappear, and the messages would all be rerouted. And so you've got a lot of scalability and a lot of resilience coming out of this architecture. And as I said, that architecture is now used by products known as web application servers in a great many modern web applications as well as CICS applications. If I can just digress just for a moment. I thought this might interest you. I don't know whether you can read that, but that's a memo written by Geoff Robinson, June 1976, the future development of the basic HICS architecture, in which, it's a 20-page memo, I won't show you the whole thing, but in which he outlines the ideas of multiple region operation, which more than anything else, I think, was actually what enabled us to leapfrog IMS. The rivalry is still strong. So anyway, I thought that this is the sort of thing, people do still have copies of these documents, which enables you to trace the history. I want to show you one more in a moment. But sadly, all the old listings and all the old software, I think, we got the latest release and the one before, but what happened to the ones in the back? I've no idea. There's not going to be the archaeology on them, I don't think. Right, so, the next thing was the idea of a transaction manager, which can manage both local transactions and distributed transactions. You heard about the two-phase commit protocol, which is what is used in processing a transaction. That was, CICS was actually the first to market with that around 1976. We had a debate about 78, I think, right, 78. We have a debate about who actually invented it, but certainly CICS was first to market with it. Sorry?
Two Jimmy Rays and Geoff Robinson, the usual ones.
Yeah, yeah. There was, yes, there's certainly a well-known US computer scientist known as Jim Gray, who lived latterly in San Francisco, who often takes the credit for it. I won't delay. There's a long story about him, but I won't delay. But I think we contributed at least as much. And it works like this. When your application has done a series of updates to databases, files, remote updates over communication networks and so on, your application will finally get to the point where it says, I want to commit all this. And to do that, it may have many different resource managers, as we call them, that it has to talk to. So this could be one database, this could be a different database. Another one of these could be a remote system. And it has to send a prepare message to each of these. And it goes the rounds, says, are you prepared? Are you prepared? Are you prepared? And when everyone finally says, yes, I'm prepared, you then send a message to each of them saying, okay, commit your updates. And when all that has happened, the transaction is complete and the application can proceed or finish or do whatever it's going to do. And this all happens transparently. You may have a huge tree of network flows taking place under the covers. The application knows nothing about it. All the application knows is you say commit, and sometime later you get a response saying it's done. And if any of these, for any reason whatsoever, is unable to commit, then the whole thing is unwound. All the updates are undone. The application is told that failed. Try again, do something different, and that's how we maintain the consistency of multiple databases, multiple resources in a transaction. There's a much longer debate about that, but it's generally recognised as a fundamental aspect, one of the fundamental building blocks of transaction processing. And then Andy talked about internal restructure. There were a number of reasons for this. Virtual storage constraint relief, we were running out of space in 24-bit addressing. Yeah. exploitation of multiprocessor hardware. The reason I mention this, these are all contemporary themes. IBM prided itself on its processors, but it turned out that Hitachi built better ones. Hitachi water-cooled processors were faster than IBM by a factor of about 2, using what was called bipolar logic in those days, which generated an awful lot of heat. And because of this, IBM just had to respond in some way, and the only way we could build processors as powerful as the Hitachi ones was to build multi-processor machines. But the software couldn't use them. In fact, it was well known that CICS ran better on an Hitachi than it did on an IBM system for a period, which is highly embarrassing. So we had to implement support for multiple processors, that was one of the reasons that we needed to restructure CICS was in order to enable internal bits of CICS to run on different processors. That was the motivation. Here's a different document. This is, there we go. So you can see these are all, this is CICS and the high end. There we go, July 1980, authors Mike Halperin and Tony Story, who you've heard of before, talking about this internal architecture of domains and how that would enable the exploitation of multiprocessors. Interestingly, in the end, that wasn't actually the solution to support multiprocessors. The multi-region architecture we talked about before turned out to be the effective way of doing it. But this whole question of supporting multiple processes is now very much a live question, as lots of software architects are talking about multi-core systems. Yeah? So the wheel comes round, and some of the solutions that they're coming up with look quite familiar. Right, so you've been very patient, and I'll try and round this off. I think Andy has said most of this, but the key point was that it turned out to be impossible to re-engineer a product that was hundreds of thousands of lines of code in one go. All you could do was re-engineer a kernel of it and set up an architecture which you could continue to use. And that process of re-engineering the kernel of CICS continues. Not the kernel, but the rest of it continues to this day. So that's, what was the date, Andy? 80 something? Well, 80 was, it was mid-80s, wasn't it? So that I think that's quite telling as well. Right. I think we talked about CICS on other platforms in a fair amount of detail, so I will just repeat the fact that when you've got CICS being able to run on different server hardware, you had this idea of a multi-system virtual environment, which I think is still a very important idea. Right, so then we got to the 90s where people were starting to demand the ability to write applications in C and C++. We started off by saying, okay, let's build a new macro processor that will work with the C language, the C compiler. But we had to follow these rules of CICS, which, if you remember, I told you disallow access to the operating system. That was very foreign to Unix programmers and C programmers who like to do all sorts of tricks. So we had to go that. Fork is the Unix command that starts up a new process. You weren't allowed to do that in CICS application. And for the guys who wanted C++, we had to design an object-based interface to replace all that pre-processing, which we did. To my mind, that probably wasn't there was an argument there about whether you design the object-oriented interface to look familiar to a CICS programmer or familiar to an OO programmer. And that was a square that was almost impossible to a circle that you couldn't square, I should have said. You need both. So that still evolves, but later we extended that for Java. The reliable message queuing product, usually known as MQ series, is one of the other hidden gems of Hursley, and as Andy said, it's become a very, very successful product. We managed to integrate that into CICS as a resource manager within that two-phase commit transaction structure. And in fact, the typical application platform that is used for those applications today is CICS plus SQL plus MQ series. And that's very widely used. And finally, the World Wide Web. In the mid-90s, this suddenly burst on the scene, and looking at it, we could see that it was a pseudo-conversational transaction-style system straight away. But that led one consultant to publish an article in which he called the web God's gift to CICS, because he saw it as, you know, finally the world's recognised that this is the right model for applications, and it's your way of doing things, so everything's fine. Unfortunately, that wasn't the whole story, because it was a competitive nightmare in the sense that everybody who could write a web application was convinced that they could do everything that you need to do for transaction processing. And in fact, of course, there are, you know, many thousands of web applications that do some form of transaction processing using a web server and a database. And for low-scale applications, that does work. For high-scale applications, it's a different matter. And there's many a web application which has looked good when tested in the lab and failed when it was deployed to the real world because of scalability issues. But it was clear that we were going to have to live in this world and that we were going to have to do something. And we came up with this idea of connectors. One of the motivations for it was to enable a web server to talk to CICS. And initially, the web provided, quite soon, the web provided this thing called CGI, which was, I don't quite remember what it was now. But it was a plug-in to the web server, which turned out to be horrendously inefficient. And so we went through, we having done one of these originally, we then evolved that whole story through many years of development, through something called the Java 2 EE connector architecture. And that was how we eventually ended up with a product that operates very successfully in that era. And it's a companion product for CICS, and it has its own revenue stream. Because this idea of plugging in is only a, if you like, a second-class way of supporting the web. And so later still, we built support for TCP/IP and HTTP and web services and all these things directly into CICS itself. So you can have a browser talk directly to CICS these days. But we had to get there fast, was the motivation. So that meant you could have this kind of architecture where web browsers would talk to a conventional web server, which using a connector here would then talk to a CICS server, perhaps on Unix or OS2 or something else, and eventually to a mainframe. And there were lots of systems around that had that kind of architecture. They're all gradually getting consolidated now. So, I think this is my last slide. We celebrated the 40th anniversary of CICS last year. So we talked about hardware that's been around a long time, but there's now software that's been around a long time, because it's not the same software. There may be some original lines of CICS somewhere in there, I'm sure there are.
Probably in capital letters.
But it certainly had a new handle and a new blade since then. And you know, this space is moving hugely fast now, but the core value proposition is still there, and is still successful. But I've no doubt there is yet more change to come. So, thank you very much. I think that's it.
Thank you, Andy. Thank you, Geoff. Questions?
Could you give us some indication of the size of the development team behind this?
Well, now
I don't know how much of it's proprietary, but could you tell us sort of what sort of job roles there are? You know, how many sort of junior, senior, etc. developers and documents and so forth?
That's a fascinating thing, because it started off with one man and a dog, as you heard, in Chicago. It was transferred to Hursley when it was only 5 years old. And the team was, we can probably name most of the members of the team, something like a dozen to begin with. Built up steadily, and Andy very clearly described the situation where we ran into huge, release 1.7, we ran into huge quality problems. And there was, just at the point when the opportunity was really taking off, and the team, I think, got to 400 at that time, in Hursley, plus all the people around the globe who are doing customer support, service, you know, fielding customer problems, all that kind of stuff. And then has gradually tapered off since then. The current team, 50, maybe, might be less. The other thing about mature products is that the management insists that you keep chasing your costs down. So you have people with very high levels of skill that are very hard to replace, you know, when they retire, or I think it's a familiar story, isn't it? So the team is not a huge team these days. In terms of individual, you know, if you counted their profitability against the revenue that they're generating against the individual heads, it would look very good indeed. But we only achieved that by being part of IBM, which has all sorts of other people and costs associated with it. I don't know if that answers the question.
Not much, but I guess there's only so much you could say. But no, actually, I'm interested. It's such a small team. That's generating $1 billion of revenue.
Yeah.
It's not bad.
Yeah.
Can I ask a second question? IBM's had a lot of activity in open source and has open sourced some of its products. What's going to happen? What's the impact likely to be of open source on CICS? And
well, that's again a very interesting question, because in its early days, CICS was open source.
Yeah.
And many customers made their own modifications to CICS. And when we, at a period in the, I think it was the 80s, we went to what was called object code only, meaning you didn't get the source any longer. And that was for all the usual reasons of we're going to protect our proprietary assets, which, you know, with hindsight, people no longer, well, there are proprietary products around. You know, you don't get to see the source code of Windows nor an Oracle database, you know. So there are proprietary products that are around. I can't see that changing. IBM does a lot of work in the open source arena. but it tends to do it in those areas where it's not the market leader.
Just a quick one. Officially, is it CICS or CICS?
Or chicks, or six, or depends which
the
country you're in.
What's the
All
official IBM term?
The US usually say CICS, the UK usually say KICS.
If you look on Wikipedia, there's a list of about 9 different pronunciations.
Yeah.
There's cheeks in Italy.
Chicks, yes, chicks.
First, a quick tale. Someone told me that the person who built Rex received many congratulatory emails, including a proposal of marriage, which of course is a Hursley product.
Yeah.
But kind of to be more serious, you threw away the line that the early versions are all lost. But about 10 years ago, I had quite a bit of email contact with some guy setting up a software museum in the States, an IBM software museum, an in-house IBM museum. As a result of which, I felt that preserving IBM software was a job being done. I take it that's not happened.
I'm not aware of that. It might be happening in the
I mean, I
US.
dredge back
I'm
into
not
my
aware
old
of it
emails
happening.
and find out who it was.
Yes, that would be interesting. I mean, it's possible that in some archive somewhere there are old copies of the software, but I have no idea what IBM's archiving policy is these days.
Somewhere in 29 embedded like tapes.
Well, I mean, there used to be a warehouse for stuff,
Yeah, well,
right, in the
there are 2
warehouse.
stories about that. Well, we owned the 2 largest warehouses in Southampton, which was full of every memo that was written in Hursley while we were going through the antitrust case. And every one of them was indexed. And
On a kickside, on a kicks TPS.
No, was it? It was, was it?
What's it called? The library system. The library index.
Oh, yeah, yeah.
And the other place was all the rest of our stuff went to the Isle of Mountain,
Yeah.
which is somewhere in the limestone caves of Cheddar.
Oh, yes, there was that. Yeah, we certainly had a large storage facility in Wiltshire, yeah. I think it was the next came along from the one where the hand bombs were kept. But I mean, it's a jolly good question, and I don't think we know the answer to that one about what is actually in the
I will
archives.
see if I can resurrect the connection.
Do.
Could I just ask you, did the guys with Amdahl and Hitachi machines get exactly the same support and service?
Yes.
Yeah, completely.
Absolutely. Yes. And that, I mean, that, again, there were many arguments and debates over lots of competitive issues of that sort. You know, when we said we're going to put kicks, the first time we said we're going to put kicks on somebody else's Unix, you can imagine there were horrendous arguments. And in the end, IBM saw sense and said, well, you know, you've got your business, you go do your business and let them do their business. And that's pretty much the way IBM Services operates these days, isn't
And
it?
of course you made your own business on the side at the same time.
Yeah, would that was so, right?
Isn't it incredibly difficult to maintain a product like that for 2 similar reasons? One, because, as you said yourself, it's now getting more and more spaghetti code. And all the people who, you know, this particular module, why was it written like that? Well, the person who wrote it like that and understood why it was written like that has now died and retired and gone away. So you no longer have the knowledge of the complexity of the system. And also because it's been maintained for such a long time, I mean, this is an experience that I'm recounting from a different system, different environment, but they found that it was incredibly difficult to maintain the team because you could, you know, if you've got some fresh graduates or something like that out of university, they'd say, well, okay, this might be interesting, it might not. They'd go there and they'd have nobody to talk to because most of the rest of the team are nearing retirement. So it's really incredibly difficult to maintain.
I mean, yes, it is difficult, but Firstly, I would say, your first point, no, it isn't getting more spaghetti code. Exactly, the code quality is actually improving as time goes by. And in fact, the error rates with CICS are very, very, very low indeed. When your customer is demanding, 5 nines, 99.999% availability on their systems, which is quite typical, you can't afford to have code errors. That means you get, you have an unexpected outage once a year, no more than that. You can't afford to have code quality problems, and the code quality is, ever since we started restructuring the product, code quality has continued to improve. Right? That doesn't mean that, when they're doing a major new release, you always have the opportunity to inject errors into it. And that's a problem for the development process. But a lot of work goes into getting quality to the right point before it's actually shipped. Extensive beta programs for months and months and months with lots of important customers. So I think that the basic point there is that actually helps to make it sustainable. The issue of handover of knowledge is, you all are familiar with that problem. That it's always an issue, but on the other hand, the profile of the team is fairly good. There is a mix of ages in it. There are people with lots of experience, and there are young people as well. And it's a special type of younger person who you can induce to work on a product that they will initially think of as old.
That's my point exactly.
Exactly. But we have got younger people working on the product, and so we have managed to do that so far. Or you can
alienated from the rest of the team.
No, I mean, of course, every young programmer wants to work on whatever is the latest thing. But what has actually happened is that they've had people who've worked in CICS for, let's say, a year or 2 years, and then ship them off and let them work on Java for another 2 years, and then bring them back and put them in CICS. And that kind of thing has been quite successful.
CICS has been very successful. Why can't Microsoft emulate that today?
They've tried. They've tried. They haven't got there yet. That's all I can say. I mean,
Windows 7 is possibly the best thing they've done.
Probably, yes. Although I have to say I only have very superficial knowledge of it. But in the 90s, when they suddenly realised that transaction processing was important, they built something called Microsoft Transaction Server, which did the core of two-phase commit and a little bit of terminal connectivity. It could do connect terminal emulators to it, and they thought that was going to do it, and they had no idea how much more they needed to do before that. They actually mounted a demonstration. They hired the Radio City Music Hall in New York, which seats 7,000, for a demonstration to the press of transaction processing on Windows, and they claimed that we are going to do 1 billion transactions in 24 hours, and using a network of Windows servers, right? And we were, and I remember the executives coming to say, oh my God, what are we going to say? And I had to write the press release. And it was, we're not going to say anything, but we're just going to say, okay, let's see if you can do it. Oh, and by the way, which bank would you like to talk to who can talk about their experience using this solution? Or which stockbroker would you like to talk to? We'll talk about their, Wall Street company. We'll give you a reference for, yes, this is a good solution. And it was a huge disaster. The press ridiculed it. Because it's quite clear, you couldn't keep one of these servers up for longer than a few hours. The degree of noise and error taking place in a network of hundreds of servers, which is what they needed, was sufficient that you couldn't possibly sustain a availability and enough to process that kind of workload, it wasn't a practical solution. And in fact, everything since then, that was almost, if you like, the peak of the idea that distributed computing is the answer to all the world's problems. Since then, the tide had been running strongly in the other direction with consolidation, virtualization. Right? Of course, there is distributed computing is still important, but it isn't the solution to that problem.
Last question.
Is Z still an important part of the methodology for KICS development and maintenance?
No. And this is interesting, which is that once we'd got enough of a specification to understand what the internals of KICS were doing and the ability to recode that, sections were recoded in Z as well as being coded in a real programming language. But once that knowledge had been diffused through the team and everybody understood how that enabled you to describe things precisely and what that meant and how you then deploy that into code and so on, we no longer needed Z. And I must confess I'm actually quite sceptical about formal methods. But that's for another day. Excuse me.
That's a cue.
There's a transaction.
Thank you, Geoff. I've lost count during your talks how many times I said to myself, I didn't know that. I didn't realise that. And that's what was very fascinating. I've been an IBM customer for 20 years of my life, mainframe. But today we had delivers with the covers on, which is a rare sight. The covers on. And finally, I am tempted to say, what was I doing on Millennium Bug?
Oh God.
I was then president of BCS. And I and the chief executive and deputy chief executive, having had media training of how to handle John Humphreys, we never did, stood by our phones over the period. And we got 3 calls, all about membership applications. That was great. Thank you very much.
Thank you.
It was a great talk. By announcing future activities. Our next meeting here is Pegasus on the 20th of May. We had hoped that would have included a bit more of this talk about Pegasus, but actually going to see Pegasus running in the museum up here. But there's certainly no doubt that it will not be running by then. Its problems continue, but we will not be. So we shall have Chris Burton. Oh, he's not here, that's right. It's a dance center, that's right. But we should put the details on the website. But it's down in Queen's Gate, across there. Speakers are Chris Burton and then Donald Sway. Donald Sway, that's right. So I hope to see you all then. There's actually another meeting in May, though it's up in Edinburgh, because we're following our newfound tradition of taking one of our meetings to Edinburgh each year to try to keep our Scottish members reasonably happy. And so on the 12th of May, Chris Burton again will be giving the talk that he gave in Manchester, the North Press Branch, and giving a fascinating insight to several of our CCS projects and how they're done. So if you happen to be in Edinburgh the 12th of May, again look on the website. Chris and I will be glad to see you there. So thank you very much again. Good to see you all. See you again next time.